force of habit, wearing my face shield. I'm the only one in the building, so I guess I don't really need to be wearing it. Anyway, welcome everybody to our third Real Analysis 2 lecture. In our last lecture, we talked about limit points of sequences. And that's going to be something that we're going to be dealing with quite a bit with the next few theorems that we do and with several examples that we give. And before we can go to our first theorem, we need to introduce the concept of a nested sequence of closed intervals. So here's our definition. The sequence of intervals with left endpoint A sub n and right endpoint B sub n. And notice this is a closed interval. We don't have the round parentheses containing A sub n, B sub n. But we have the square brackets or braces containing A sub n, B sub n. So these are closed intervals. A sub n and B sub n, those endpoints are contained in each interval. So a sequence of intervals, closed intervals, with A sub n left endpoint, B sub n right endpoint. And here we list the intervals in roster form. This sequence of intervals is a nested sequence of closed intervals, exactly when two conditions are satisfied. The first condition is that the interval A1, B1 contains the interval A sub 2, B sub 2, which in turn contains the interval after it, and so forth and so on. You might look at this symbol and say that it looks like the notation for subset, except it's turned around. So instead of this interval being a subset of this interval, A sub 2, B sub 2, is a subset of A sub 1, B sub 1. Or we could say A1, B1 contains interval A2, B2, which contains the interval that comes after it, dot, 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 which contains the interval A sub n, B sub n, and so forth. Now, we could describe this another way. We could say that the interval A sub n, B sub n contains the interval A sub n plus 1, B sub n plus 1. In other words, every interval in this sequence contains its immediate successor. Every interval in this sequence contains its immediate successor. So that's the first criterion. Every interval in the sequence contains its immediate successor. The second criterion is that the limit as n goes to infinity of b sub n minus a sub n equals 0. And if we think about what b sub n minus a sub n represents, the significance will become obvious. Here's the nth interval with left endpoint a sub n, right endpoint b sub n. What's the length of this interval? Don't we compute the length of an interval by taking the right endpoint b sub n and subtracting from it the left endpoint a sub n? So b sub n minus a sub n is the length of the nth interval. So what we're really saying here is that as n goes to infinity, the length of the nth interval goes to 0. So if these two criteria are satisfied, then this sequence of closed intervals is called a nested sequence of closed intervals. And before we do a theorem or anything like that, let's just play around with a few examples, okay? Okay, let's look at this example. That we have the sequence of closed intervals with left endpoint 0 and right endpoint 1 over n, where n goes from 1 to infinity. So notice that the left endpoint of an interval is also the same as the left endpoint of its successor. So the left endpoint of every interval is contained in, I'm sorry, I'm doing this backwards. Notice that the left endpoint of every interval is 0. So the left endpoint of one interval is the same as the left endpoint of the interval that came before it. So every interval's left endpoint is contained in the interval that came before it. Now, can we say the same thing about the right endpoint? Well, let's see. The right endpoint of every interval is less than the right endpoint of the interval that came before it. So every interval after the first is contained in its immediate predecessor, or each interval contains its immediate successor. So the first thing, every interval contains its immediate successor. They have a left point in common. And the immediate successor's right endpoint is less than the immediate successor's right endpoint is less than the right endpoint of the interval that we're referring to. So this interval is contained in this one. Every interval is contained in its predecessor. Each interval contains its successor. So this is satisfying. Now let's see. Is it true that as n goes to infinity, b minus a goes to 0? Well, let's see. What are we really saying here? We're saying the limit as n goes to infinity of the right endpoint minus the left endpoint is 0. So right endpoint minus left endpoint equals 0. Okay, check. Now that's one example. Let's play around with one or two more. Okay, let's take another example. Here for all natural numbers n, the left endpoint of the nth interval is -1 over 2 to the n minus 1. The right endpoint is 1 over 2 to the n minus 1. So if n is 1, we have n minus 1 is 0. So we have 1 over 2 to the 0, that's 1 over 1 is 1, with a negative sign out in front, -1. Here we have 1 over 2 to the 0, that's +1. So this is the interval for n equal 1. For n equal 2, we have 1 over 2 to the 2 minus 1, or 1 over 2 to the first. Negative sign out front. So negative 1/2 is the left endpoint, and positive 1/2 is the right endpoint, and so on and so forth. Is this a nested sequence of closed intervals? Does each interval contain its immediate successor? Let's see. A sub n, B sub n, what is that? Well, that's this thing right here. And this thing, this is negative 1 over 2 to the n plus 1 minus 1. 1 over 2 to the n plus 1 minus 1. So that's 1 over 2 to the n. Now, how do these endpoints relate to these endpoints? Notice that the left endpoint of the n plus first interval is negative 1/2 times the left endpoint of the nth interval. So the magnitude of the left endpoint of the n plus first interval is 1/2 the magnitude of the endpoint of the nth interval. And it's also true the right endpoint of the n plus first interval is 1/2 the magnitude of the right endpoint of the nth interval, which essentially means that since the left endpoints are negative, the left endpoint of the nth interval is less than the left endpoint of the n plus first interval. The right endpoint of the nth interval is greater than the right endpoint of the n plus first interval. So we can do this. And if we have our doubt, let's just look at the pattern. First interval, negative 1, 1. Second interval, negative 1/2, 1/2. Third interval, negative 1/4, 1/4. The magnitude of the endpoints is cut in half with each succeeding interval. So yes, each interval is contained in its predecessor, or every interval contains its immediate successor. So the first condition is satisfied. Let's look at the next condition. And does the limit as n goes to infinity of b sub n minus a sub n equals 0? Well, here's our b sub n, here's our a sub n. Okay, as n goes to infinity, 2 to the n minus 2 goes to infinity. So the length of the nth subinterval does go to 0. And here we'll answer a resounding yes. So this is also a sequence of this is also a nested sequence of closed intervals. Just for emphasis, we'll just put down in writing what it is that we just confirmed. This sequence of closed intervals is a nested sequence of closed intervals. I smell a theorem coming up. Okay, here's our theorem. Interestingly enough, it's called the nested interval theorem. So this is going to be one of those that we have to memorize. Suppose that a sub n, b sub n is a nested sequence of closed intervals. Then there exists a unique real number p such that p is in the intersection of all of the intervals a sub n, b sub n. So if we take all of these closed intervals, each interval snugly contained inside of its predecessor, if we take all of these intervals and take the intersection of them, their intersection turns out to be exactly 1 point, p. So let's see. First of all, there exists a real number p that's in this intersection. So the intersection is not empty. Secondly, there's exactly 1 real number that's in this intersection. Now we get to prove it. And I'm going to hit the chicken switch as I usually do. Just to get the ball rolling, I'm going to state the hypothesis and maybe even elaborate on what the hypothesis means, just so that I can get myself off to a good start. Okay, I wrote down my hypothesis, and then I explained very explicitly what my hypothesis means. I just did that, one, to make myself acknowledge what the hypothesis really was, and two, just to give me a starting point for my proof. Now let's see where we can go from here. I'm going to make this observation in general about our left and right endpoints. Our intervals are such that, let's start here. A sub n is less than or equal to a sub n plus 1. And b sub n is less than or equal to b sub n. This is how the n plus first interval is contained in the nth subinterval. So in order for this interval to be contained in its predecessor, a sub n, b sub n, a sub n has to be less than or equal to a sub n plus 1, and b sub n plus 1 has to be less than or equal to b sub n. And all of these intervals fit inside the first interval, a sub 1, b sub 1. So all left endpoints have to be greater than or equal to a sub n, and all right endpoints have to be less than or equal to b sub 1. Now, why did I write this? I wish I knew. No, just kidding. There are going to be two observations that I can make from this. You see this in general, a sub n plus 1 is greater than or equal to a sub n. So if we just look at the sequence of left endpoints, a sub n, this sequence of left endpoints is monotone increasing. But there's also something else. Every left endpoint, a sub n, is less than or equal to b sub 1. So this sequence is monotone increasing and bounded above by b sub 1. And give me a chance to erase some of the board.